Okay, thanks for joining us for the Western Wheels Conference. A couple quick things before we begin. If you need a certificate, you'll find the link for that here. You'll need to submit a separate request for each session that you attend, and you should receive your certificate in email within 24 hours of submitting the request. If there are any handouts available, you'll find those there. And if you're interested in learning more about any of the products featured in our sessions, that'll take you to the product page for each one. And if you click request pricing, that'll add it to your wish list. Here we are at the wish list. You can either complete the form and submit it right away, or you can keep browsing around and adding items to it to get one big quote. And you can always get back to your wish list right up here in the top right-hand corner. That's it. I hope you enjoy the session, and we'll see you on the other side.
Hi, my name is Rory McLaren with the Fluid Power Training Institute, where we build the best hydraulic training systems in the world. Hydraulics, pneumatics, and electrical. First and foremost, for any of you in the audience that have served in the military, on behalf of the Fluid Power Training Institute and DACTIC, we thank you from the bottom of our heart for your service to the country and to the world. I also want to thank DACTIC for inviting us to participate in this program. So thank you, my friends at DACTIC, for the hard work you do to promote our products. Today, I'd like to talk to you about microleak testing. That's the focus of our presentation. And microleak testing is nothing less than revolutionary. I am a proud Red Seal diesel fitter. I served my apprenticeship in South Africa, and I earned my Red Seal after 4 years. I was indentured as an apprentice with a company at the time, Galleon South Africa, and Galleon at the time was probably one of the most notable manufacturers of rollers, graders, and cranes in the world. So my background, I started out with construction equipment. I could see very quickly after I graduated and I went into the training department, I could see that there was a problem. And that problem on the equipment was hydraulics. Even though I did 4 years of engines, I could see that we didn't have engine problems per se, that most of the field calls that came to us from our field service technicians were related to difficulties with diagnostics. And it wasn't always that they didn't have the skill set to do the troubleshooting, as much as it was that oftentimes it was impossible to get the diagnostic equipment into the circuit. What I did was I identified, when I started using a flow meter, not only did I figure that they were impossible or almost impossible to get into the lines. I mean, think about it. If you're going to put a flow meter in a line to test a pressure relief valve or to test a cylinder or to test a directional control valve, it's not going to happen. Certainly not when you've got, let's say, a valve where your directional valves and your pressure relief valves share the same body. They're integrated. How are you going to differentiate where the problem or isolate the problem in a case like that? So that was a challenge. The other problem is that, and we need to understand this clearly, whenever there is a speed problem on a hydraulic actuator, actuator is the collective term for cylinders and motors. When an operator complains that the hydraulic cylinder or motor is slowing down, understand this: it can only be a flow-related problem. It cannot be a pressure deficit. It's impossible. In other words, you will not find the problem with a pressure gauge. Most people who work on hydraulic systems have a pressure gauge, but they don't have a flow meter. The number one problem, however, is flow related. Since it was so difficult to get a flow meter into the line, number one, and number two, a flow meter, the scale on a flow meter does not jive with the kind of leakage rates we're looking for. In other words, when you have leakage across a pressure relief valve or a directional control valve or a cylinder, that leakage that's causing the hydraulic system to heat up or causing an actuator to slow down could be minuscule. In other words, if you take a 0 to 50 GPM flow meter, whether it's analog or digital, the amount of oil that you're looking for is not on the radar screen. In other words, a 0 to 50 analog flow meter will only start reading flow at 5 gallons per minute. So there you have a problem. What I decided to do was a study. I embarked on a study of leakage rates in hydraulic components. And I was lucky enough to do it for a decade. So what I did was I took brand new components and I measured their leakage rates against components that were worn out. In other words, what I needed to do was determine at what threshold a hydraulic component becomes useless. I had to figure out a way to pressurize the chamber in such a manner that it would not mask leakage. In other words, I had to pressurize a chamber in order to see if the chamber was leaking. Bear in mind that your pressure relief valves, check valves, etc. are zero leakers by design. So by pressurizing the chamber, one could figure out if there was a leak or not, because obviously if it maintained pressure, it wasn't leaking. But if it started to lose pressure, it was leaking. Now that oil had to be pumped in by a manual pump, a hand pump. It couldn't be pumped in by let's say a power source. That wouldn't work. You couldn't maintain pressure on it. And I'll show you what I mean by this. Let me demonstrate that. It's easier to see it than it is to try to visualize it. In the long run, what I did was I developed Microleak testing, the standard for testing those components which are difficult to test in the field. So that's what our presentation today is about. Would you buy a product if the failure rate was over 95%? I guarantee not. In other words, if there was a rumor that a certain component had a 95% failure rate, nobody would ever buy the component. Well, I'm sorry to say that the product that we're producing out of our technical colleges, that is fluid power technicians, their failure rate to diagnose hydraulic components and test the performance of hydraulic components is a dismal 95%. In other words, that is the failure rate. Colleges are servants of industry. What a college should be doing is going down to the local businesses and asking them, where is your problem? Where is your Achilles heel? And you will quickly learn, because I work in every industry, oil field, forestry, aviation. The Achilles heel is hydraulic troubleshooting. Go to any company and ask them, what is the number one skill set you'd look for in a mechanic seeking a job at your facility? And they'd be saying, we've got hydraulic systems, but we can't find people that can troubleshoot them. Well, there must be a big disconnect here. Most of the colleges in our country teach hydraulics. So where's the disconnect? How is it possible that with so many colleges, we have a critical shortage of competent hydraulic diagnostic technicians? The problem lies in the curriculum. The problem lies in not the talent we have or the brilliant instructors we have. The problem lies inside of the curriculum. We do not have a curriculum that will nurture a competent fluid power technician. I know that because I travel to colleges and schools for a living. I go to these schools and colleges and I see the curriculum. We've already established that hydraulic systems are not designed to facilitate proactive maintenance and troubleshooting, which is why I invented Microleak testing. It's a way to test a component when all else fails. Again, less than 1% of the students that graduate from fluid power programs are competent to troubleshoot hydraulic systems. And I get this from all corners, the rental industry, every industry. They're all having the same complaints. The hydraulic troubleshooting error rate, I call it the HTER, is 85%. That's a conservative estimate. This means that over 85% of the components removed from hydraulic systems are in perfect working condition. I had a client recently call me from a mine in Nevada that had a problem on a hydraulic system which cost them ultimately $167,000 to fix. They replaced every hydraulic component on the machine. It's disgraceful. It was an elementary problem. They have good, hard-working technicians. They just don't have the skill set to find the problems. So let's see if we can solve this problem. When I go up to a component, let's say, for example, a pressure relief valve over here, and I'm going to troubleshoot it. I'm going to demonstrate to my students how to troubleshoot it. I ask them before I embark on the procedure, have you ever had reason to believe that a relief valve was defective, leaking internally? And they said, yes. I said, what did you do? They said, replaced it. Folks, that's 97% of the answer. So I give it a margin of error of 15% only because some of the students don't like to vocalize. So those numbers come from the horse's mouth. All these numbers come from maintenance people that I talk to. On the simulator, we have a Microleak test pump. Now, before I move forward, let's understand that a Microleak test pump is specifically designed for the purpose of Microleak testing. Do not substitute this pump with a porta power for two reasons. One push of the handle on a porta power will put you at 10,000 psi. What if you're testing a 1,500 psi rated valve with a 10,000 psi pump? Somebody's going to get hurt. First problem. Second, it took me a long time to figure out how much oil to deliver into this chamber I'm talking about so that I didn't generate either a false positive or a false negative. In other words, take a directional control valve, for example. It's a sliding spool valve. It's got a spool inside that slides back and forth. Clearly, if the spool can move, there must be a clearance, and if there's a clearance, there's going to be leakage. So, imagine that I had a pump that pumped so little oil that it couldn't make up for the leakage in a brand new valve. It would give me a false positive. It would tell me that the valve is, let's say, bad when the valve is actually good. Let's go the other way. What if I put so much of flow into the valve that I could make up the leakage when the valve was bad? Then I'm back in square one. So the volume that is displaced with the Microleak testing is critical to a good outcome. The Microleak test pump's pressure relief valve is set at 3,000 psi. Now, the Model 102 comes fully equipped with a Microleak test pump, and the pump that you have on the simulator is different to the one you would have in the kit only because it is filled automatically from the rear. The student does not have to fill it up. When we designed the Model MF102, the trainer you're looking at here, we wanted to make it so that the wear in the valves was realistic. In other words, it is very difficult for a student to learn how to troubleshoot leakage in components when they have to imagine the component is leaking. Imagine the pump is worn out. Imagine the directional control valve is worn out. Imagine the pressure relief valve seat is worn. So what we did is we made it possible for every single component, or let's say almost every component on this MF102 trainer, to leak in real time. So through the computer, we can make these components morph from being in good working condition to being worn out. And I made a point in designing these trainers to make sure those leakage rates were identical to the leakage rates in the field. In other words, the transition from the lab to the field is seamless. Now, if you don't have a model MF102, all is not lost. We can still teach microleak testing. So don't give up. All we've done with the MF102 is made it easy. I'll show you how. All right. Now, the microleak test system on here is very simple and straightforward. It's a little pump. It's got a knob on it. You just open and close it to generate pressure. And then, of course, all you have to do is pump in order to operate the device. It's very simple, very straightforward. Try to imagine that you're in the field, you've got a little pump, that's all you need. Now in the kit, the microleak test kit, you'd have adapters that would adapt you into the port that you were going to test into. And the adapters are in all shapes and sizes. You've got NPT, you've got JIC, you've got J1453, and split flange. So there's no shortage of connectors. One of the other advantages of microleak testing is it's almost non-invasive, almost. To test most components, as you will see, I only have to remove one transmission line. Now, safety. Make sure whenever you're going to work on your hydraulic system, number one, that you lock out the system in accordance with your company's policy, or in accordance with OSHA's lockout standard for the control of hazardous energies. And then, at the point of entry, you must make sure there is no stored energy. A hydraulic system has the unique ability to store energy cells after shutdown. So at the point, I call it the point of entry, the POE, what you want to do is make sure that at that point where you're going to take a line off or take a component off, the system is in a zero energy state. That's critical. And if you're not sure how to do that, you need to have a conversation with the respective manufacturer. But those are your responsibilities to make sure the system is safe to work on. What I'd like to demonstrate going forward here is, let's start with a simple thing like a directional control valve. If I have let's say a forklift, because if I got a vertical downdrift on a forklift, there can only be two components which can cause the problem: the cylinder and the directional control valve. There are no more suspects than that. So we're going to focus on the directional control valve, which quite frankly is the easiest component to focus on. Looking at the inside the valve itself, you can see that this B chamber here is completely enclosed. It's closed. So is the A chamber. When I raise the forks on a forklift and I go back to neutral, I want to hold the load. So the valve has to be closed. The ports have to be closed. Well, if I've got a vertical downdrift, then I suspect that I've got wear between the spool and the bore. So that's my target. And that's what I'm going to show you how to isolate here. When I invented microleak testing, I wrote a book about doing these various tests. In fact, I wrote a book that I call Standards for Testing Hydraulic Components. And what I did was obviously as a field reference guide to troubleshooting, That was, let's say, what I needed to develop. But in addition to that, we needed a student workbook. I also show what are the main causes of problems in hydraulic components. And of course, if you read any literature today, they say that 90 to 95% of hydraulic component failures are, of course, contamination related. So let's focus on the problem that you're most likely to find in the field. These are the kinds of activities. What the student will do is the student will build a circuit. There's a hydraulic cylinder, there's your valve, the two A and B ports are closed, and what will happen is the student will build the circuit, set the various valves, and then of course when they go to the next screen, what will happen is it'll automatically introduce the fault. In other words, the cylinder will be drifting in real time. I'm going to go to the instructor login on the computer, and I'm going to go in to the faults here, and I've got the manage faults screen up. And what you see is you see a list of all the components on the simulator. What we want to do is we want to create a fault in the directional control valve to start with. So let me just connect up this line over here from my pressure relief valve to the tank, and I'm going to just turn the knob in a few turns. If I was going to bench test the valve, I'd basically turn the knob in a few turns, and then I'm going to conduct the test. Now, whenever we're testing, the most critical thing we need is we need to wear safety glasses. Safety glasses. Never work on or around a hydraulic system without safety glasses. The oil, all the oil wants to do is come out at you. And if it does, and it strikes you in the face, in your eyes, it's going to be ugly. So let's wear our safety glasses. Now, there are a number of myths associated with testing hydraulic components that exist in the industry. You'll read them in manufacturer's literature, you'll read them in all kinds of literature. And myth number one, when we talk about pressure relief valves, is if you can set a pressure relief valve at its predetermined pressure, it's in perfect working condition. That's a myth. I understand that that can't be true only because I understand how a pressure relief valve works. In other words, a pressure relief valve is a zero leaker by design. So if for example, if I've got a leak in a pressure relief valve, then it's obviously a problem. If, let's say, 3 to 5% of the oil is leaking across the seat of a relief valve when it's closed, doesn't the other 95% have to open it or shift the spool in order to pass through the valve? Well, if you can shift the spool, you can set the valve. So that classifies a pressure relief valve as a leaker, or as a zero leaker rather, but beware, because if I can set the valve, it doesn't tell me that the valve is defective at all. All right, now we'll come back to the pressure relief valve in just a minute. So now what I'm going to do is I'm going to start the unit and I'm going to raise the load. So let's do that. I'm going to start the unit up and I'm going to raise the load. All right, as you can see, if I stop, it holds position. Everything is fine. So imagine that now I've got a situation where I'm teaching a student how to troubleshoot a cylinder on a forklift, and that's basically what it looks like. Now, what I'm going to do is let's lower the load. All right? And now what I'm going to do is I'm going to create a fault in the directional control valve in real time. I'm going to make it leak in real time. So I'm going to go to the directional control valve. I'm going to select both ports, and now this valve is leaking internally. Now, in the activities, and I'll go over this briefly later on, in the activities, the student will actually graduate from here. The student won't be using this screen. This is a screen is mainly for, let's say the instructor wants to simulate a problem on a machine outside of, let's say, the circuits that we've developed. Well, then the instructor can go in here, generate the fault, and then shut the screen off. The fault remains, and then the student goes and looks for the problem. Most of the troubleshooting is tailor-made. We've already done it, and we focus on the main problems, as you will see. I'm going to raise the load again. Okay, and I'm going to go to neutral. As you can clearly see, I have a vertical downdrift in real time. So, the idea here is to show you how simple it is to test the directional control valve. What we do when we go into the field to test this valve is we look for the line coming out the bottom port of the cylinder, and we see to which port it is connected in the valve. In this case, it's connected to my port B. If I was in the field, and let's say this was a JIC 37 degree, I'd screw it off. I'd put my adapter in place. Remember, I'm locked out, I'm tagged out. I've de-energized and I've verified, and I'm going to pull just the suspect line off. That's all I'm taking off. I'm going to use my Microleak tester to find out if my directional control valve is leaking. The first thing I want to do when I use my Microleak tester is give it a Microleak test first. This is how simple that is. I want to make sure that the reason why I'm seeing a decrease in pressure on my gauge is not because I'm leaking inside my Microleak tester. That's the first thing I have to do. So here's what I'm going to do. I'm going to pressure up, and as you can see, I've got resistance, the pressure's building, I'm about 900 psi, and I'm holding. That means my Microleak tester is in good condition. All right, so now I'm going to take a hose from my hose tray here and connect it from the Microleak tester to the suspect port in my directional control valve, which is port B. That's all I've done. Remember, this machine is locked out. We've de-energized and verified. We're about to find the problem. You'll notice in the field, this will take no more than about 15 minutes. 15 minutes to find and isolate a problem in this particular instance. Now I'm going to close the valve on the Microleak tester, and I'm going to pressure in, or at least attempt to. Notice that there is no gain on this pressure gauge, nothing whatsoever. Now you might be saying, well, what does it look like when the valve is good? Well, let me show you. Let's take the fault out. The fault's gone now, and let's do it again. The minute you take the fault out, when the valve is not leaking, you'll immediately build pressure. And since the valve's a leaker by design, you'll notice that it'll slowly bleed down. The mere fact that I got resistance tells me the valve is in perfect working condition. Conclusion. If I was in the field and I had a vertical downdrift on a forklift and I did this test, and let's say the outcome was that I built resistance against my pump, then of course I'm going to automatically replace the cylinder. Why would you test the cylinder? There's only two suspects, so obviously you know where the problem lies. If, however, let's say it didn't pressure up, well then you have still, here's what you want to do. You now know definitively that your directional control valve is leaking, but don't put egg on your face. What you don't want to do is order a new directional control valve to find actually the cylinder was also leaking. No, what you want to do then is you want to do a cylinder test, which I'll show you in just a moment. So, once again, very simple, very safe. I'm either going to find the problem in the directional control valve, or I'm going to find the problem is in the hydraulic cylinder. We actually have real machines. They're generic, but they're real machines. And so it says the forks drift down when I put the directional control valve in the hold position. The problem only happens when there's a load on the forks, and the problem seems to be getting worse every day. The student will then build the actual circuit that you'd find on a forklift. I'll go to the next screen. What I've done is I've actually now introduced the problem. And what's really cool about the MF102 is that the student can actually fix it. If I find the directional control valve is leaking and I touch the symbol for the directional control valve on the screen, it'll draw it out of inventory and put it on the machine. See, it's gone. Now, when the student starts the machine, the student will have repaired the forklift, and it'll give them a report. When I finish it, it'll tell the student whether they have they've been successful in finding the problem or not. So that's how simple and straightforward it is. Again, we've got an assortment of machines. We've got some 50% of the circuits are we call them industrial, and 50% are mobile. Here's something really, really cool, and that is when we are troubleshooting stacked valves. So what I'm looking at here now is I'm looking at a stacked valve assembly here. Stacked valve. What we mean by that is you've got a subplate and all your valves are stacked on top of one another. I'll show you the circuit for that in just a moment. Whenever we're going to work on a hydraulic system, be it mobile or industrial, we need to isolate the power source, and we need to make sure that at the point of entry, we're in a zero energy state. Absolutely critical. Otherwise, we're going to have a bad outcome every time. All right, just a reminder about safety. What we're going to do now is troubleshoot this valve, the stacked valve assembly, because we have, let's say, a vertical downdrift on the cylinder. Every single time I have asked a student, do you have reason to believe that you have leakage in a stacked valve assembly? Every single time, without exception. The answer has been, if I did suspect a problem in there, I replaced the whole valve, the whole thing. 1, 2, 3, 4, 5 valves. Can you imagine the numbers of valves that are thrown away every year because we can't troubleshoot, find simple problems in these valves? Here's the hydraulic circuit for that stacked valve assembly. As you can see, what they've done is, and the industrial people typically do this, although you'll find this on a lot of mobile equipment, is you've stacked the relief valve on top of another relief valve, on top of a flow control valve, on top of a pile-operated check valve. And of course, the directional control valve always goes to the top. First and foremost, if you ever disassemble one of these assemblies, you must mark them so they go back in the same position. Now, I'm going to start out by talking about what happens if, for example, this cylinder rod is drifting out. Suspect number one is, of course, my cylinder, and I'm going to follow the oil flow from here up into the valve, and you'll see it goes up there through the flow control valve, and there's suspect number 2. I'm going to test this valve. All I have to do to test this valve is take my Microleak tester and, again, lock out, tag out, de-energize, verify, and I'm going to hook my Microleak tester up to port B. And I'm going to attempt to pressure up. If it doesn't pressure up, I know for a fact that this valve is defective. How long did it take me to find that? 15 minutes? About right. If, for example, when I pressured into this valve here, it didn't pressure up, then of course my cylinder is also a suspect. So it's a very, very simple and effective way to find leakage rates in hydraulic components. I'm going to look at the components that are more challenging. Directional control valve testing, there are many textbooks, and we need to be very careful about what is in the content of textbooks that we hand out to students. I highly recommend that instructors discard any information that tells a student to pull a line off and start a hydraulic system up. And you'll see this is common, especially on directional control valves. You'll see it on cylinders. You'll see it on case flow testing. Take the line off and stick in a bucket. Folks, it is highly, highly hazardous for many, many reasons. This is not the right way to test hydraulic components. In fact, I have sometimes had the opportunity to be involved in actual investigation and reconstruction. I've seen what happens when we discharge hydraulic oil to the atmosphere. It can cause burn injuries, eye loss, blindness, severe eye injury. It can cause oil injection injury. Bear in mind that the normal operating temperature of hydraulic systems, normal, is above the threshold typically that'll put you in hospital with second and third degree burns. Not only are we risking life and limb, but what if that oil, as it has happened in many times, finds an ignition source, a turbocharger, a heater, and all of a sudden now you have a fire. There is no reason to ever discharge hydraulic oil to the atmosphere for testing hydraulic components. Let's turn our focus to what we call a mobile directional control valve, mobile. So I'm looking now at this valve here, which you'll find on forklifts or front-end loaders. Once again, before I show students how to troubleshoot this valve, I ask the same question. Have you ever had opportunity to believe that there was leakage inside one of these valves? And if they say yes, my question is always, so what did you do? The valve was replaced. Now, this valve is loaded with associated valving. A typical mobile directional control valve, as you can see in here, has load check valves, it has anti-cavitation valves, it has cylinder port relief valves, and of course it has the spool and the bore. So the number of opportunities for this thing to leak are in abundance. In other words, if I've got a vertical downdrift, and let's say I follow the line from the cylinder into this port here, where am I leaking? Is it leaking in the anti-cavitation valve, the cylinder port relief valve, which by the way is a combination valve typically, or is it leaking through the spool and the bore? Well, that's the problem. In my experience, in my troubleshooting experience, 98% of the time, the problem was in the cartridge valve, not in the spool and the bore. In other words, it's a very, very simple problem to solve. Let me show you how. Let's say I've got a vertical downdrift on a cylinder and I follow the line to this port here, all right, which means I'm going to focus on this area here. All I have to do is take my Microleak test pump, take the appropriate adapter and connect it to the port here. Remember, the machine is locked and tagged, and you've made sure that at the point of entry, you're in a zero energy state. I connect my Microleak test porter and I start pumping, and what I find is it doesn't pressure up. Well, where's it leaking? It could be leaking through the seal, through the seat, through the anti-cavitation valve, or through the spool and the bore. So, how do I isolate that? Well, that's easy. You either have a valve across in the other port that's identical, or it could be different. It doesn't have to be the same. This could be a combination cylinder port relief anti-cavitation valve. This could be simply an anti-cavitation valve. Nonetheless, I'm looking for a good valve to replace this valve with. So all I do is I Microleak test this port, and if it pressures up, it confirms that this valve is in good condition. So what I do, I take this valve out, I replace this valve with that one, and I repeat the test. And 98% of the time, it's going to pressure up, which means that you haven't replaced the whole valve. And when I say replace the whole valve, I'm not talking about just a section. I'm talking about, if this is a 5-bank valve, this is a 10-bank valve on a mobile crane, this whole thing's coming off. This is a day's worth of work. It's an absolute waste of time and energy. So here I'm able now to pinpoint the leakage path inside the valve and find out exactly where the valve is leaking. Now, I've got asphalt paver, I've got a front-end loader, I've got all kinds of equipment here. What I'm going to do is I'm going to go to the front-end loader just to make my point. And here we've got two of the most common problems on a front-end loader. Either the dump rollback is drifting or the raise lower is drifting. Let's go to raise lower is drifting. There's my front-end loader. It tells me what the problem is, what the operator's complaining about. I go to the next screen. I build the exact circuit that you'd find on this front-end loader. So you build it with this valve. When the student finishes all the setups and raises the load, it'll hold position. However, when the student goes to the next screen, there'll be some instructions, and then it'll auto-fault, meaning that the next time the student raises that cylinder, it's going to have a vertical downdrift in real time. So, what the student will be doing is be testing that valve to find out if it's spool bore wear or the cartridge is worn. And when the student finds the defective valve, when he or she touches that particular section on the valve, it says, do you want to test the valve or replace it? Well, I want to test it. What kind of test do you want to do? A microleak, a flow test, a pressure test. This gives the instructor the opportunity to see if the student is choosing the right technique. I'm going to do a microleak test. It's obviously going to see how long it takes the student to do the activity because the clock is now running. It's in motion. And I'm going to say, okay, I've done a microleak, I'm done. Test passed, test failed. Let's say the test failed. Do you want to keep the valve or replace it? I'll replace it. And it'll ask you again because you don't want to default or create a false negative or a false positive. So it'll ask you again, do you want to replace it? Yes, I do. And you're done. And then when the student is finished with the activity, when he or she is finished, what it'll do is it'll say, something else needs to be done. The hydraulic system is still defective. Continue the repair until the hydraulic system is operating properly. So it'll either tell the student that he or she was successful in finding the problem or that they need to move on and continue to look for the problem. And it'll also give you a summary of what's been done. All right, so once again, we've got some realistic machines. Here you can see a long reach forklift. And what I'm doing is the boom is slowly drifting down. And of course, the student is going to solve the problem. Another advantage of the model MF102 is, let's say your students are graduating from your school and they're going down to a local, let's say there's a local forklift manufacturer and they're going to go and seek employment there. What you can do is you can go to that forklift manufacturer, and if they're kind to you, they'll say, yeah, here are our schematics. With our help, you can put those forklift schematics into your computer. And here's what will happen. Your students will graduate and get hired by that local forklift manufacturer, and they will know more about troubleshooting the systems on those forklifts than the mechanics that work there do, because they won't know microleak testing. So it's a win-win for everybody. Let me now show you how to test a hydraulic cylinder. Once again, folks, do not attempt to troubleshoot or repair a hydraulic cylinder without training. Many times people have done this and they've got into trouble. I highly recommend to instructors that you teach students about all of the various types of cylinders that are available in the marketplace. Here's an example. I was involved in an accident investigation in which a cylinder repair person was fatally injured because he did not know, he was not trained, he did not know that inside the rod of the cylinder was an accumulator. He didn't know that. And he took the piston off. It killed him instantly. So, in other words, let's say a student is going to go and work for a ready-mix concrete truck company, and they don't know this, and the company says go and repair the cylinder. I think it's very important for the student to understand that on some rear discharge concrete trucks, especially, the accumulators inside the cylinder rod, they need to identify with that. In other words, we need to show them that if they see a valve that looks like the valve on an accumulator on a cylinder, that means that should be an alert to say that there's potentially compressed gas inside the cylinder. So it's really important to introduce students to all the various types of cylinders, and we try to cover all these bases in our safety training, which is part of the curriculum. Here's another thing you'll see and you want to avoid is where you've got, for example, you've got a situation where, and this was recently told to me in a workshop, where they actually will take a hydraulic cylinder that is they're having difficulty taking apart, and they'll actually connect cables to it, and they'll try to pull it apart. Well, in this instance, what happened was, because a cable or a chain will recoil, the piece of the cylinder actually hit the rear window of, I'm not saying it went through, this is just an illustration, but it hit the rear window of the vehicle. And that's basically what can happen when we start using these substandard procedures to try to disassemble a cylinder. A very common technique is to use compressed air. This is probably, when we look at the most dangerous things you can do with a hydraulic system, this is right at the top of the list. Never, ever introduce compressed gas into a hydraulic cylinder in an effort to push the piston out from the inside. It's just a really, really bad practice. Its potential is immense. Let me give you an idea. Here's a hydraulic cylinder that these folks are trying to take apart, and they've got compressed gas in it. This is what a missile. This thing is lethal. Watch what happens. Let's do it again in slow motion. There is no doubt that if a person was standing in front of that rod or behind that cylinder, the cylinder itself, there would have been either a very severe injury or a fatality. So once again, it is absolutely critical that we understand when it comes to cylinder testing how to do it safely and effectively. And once again, let's look at microleak testing as a solution. It is very common for even manufacturers to say, if you want to test a hydraulic cylinder, do this. Push the cylinder rod all the way out, remove or disconnect the line from the opposite side, and pressurize this side, which means we're back to testing to the atmosphere. I've noticed that most of the companies that tell us to do this don't tell us in which direction to run the test. They don't tell you. In other words, I can see this cylinder has two seals. If, for example, it's vertical and it's drifting down, the rear seal is my suspect seal. What if I retracted the cylinder, pressurized the other side, and pressured in, and it didn't leak out the other side? That would tell me the cylinder's fine. Well, I'm on the wrong side of the problem. The suspect seal is the one on the back, not the one on the front. Takeaway here is when you test a cylinder, you always test in the opposite direction to which you are drifting. In other words, if you're drifting down, you test going up. I investigated an incident where the student was following the manufacturer's recommendations, or at least the technician was, and he took the line off the live end of the cylinder, pressurized into it, and it did have a bad seal, or at least bore. There was a gas heater above the machine. The oil went straight up. Of course, it's highly volatile. It's atomizing, and it burned the company to the ground, the whole company. This is what happens when people are taught how to do things the wrong way. Never remove a hydraulic line for the purpose of troubleshooting the component. It's dangerous. It can cause severe injury, death, or substantial property damage. There's a gentleman that talks about plugging the port at the live end of the cylinder here, retracting the cylinder rod, plugging the port, and then if the seal's leaking, then it will regen regenerate out, meaning it'll equalize pressure on both sides, and because of the area difference, it'll push the cylinder rod out. Don't even think about making that recommendation. That thing is going to be problematic from 2 points of view. One is, let's say the cylinder is rated for 3,000 psi, max operating pressure. And let's say that the cylinder rod to bore ratio is 2 to 1. If I have a difference in area here of 2 to 1, meaning this area here is twice the size of the area in the opposite side, then this is what's going to happen. If I plug the port on the live end of the cylinder and I put 3,000 psi on the major area, the large surface area here, the pressure on the other side is going to go up to 6,000 psi. That's 2 to 1. A hydraulic cylinder is both a pressure amplifier and a flow amplifier. Can you imagine if this is rated for 3,000 psi and you're going to 6,000? Somebody's going to get killed. Next problem. Back to square one. It's got two seals. If the front seal is not leaking, it can't regen out. So if the rear seal is leaking, it's not going to detect that. The only way this is going to work is if the bore is damaged. But once again, you're going to get a false positive or a false negative. It's pointless. Let's not do that. Let's do a Microleak test. Let me show you how. Here's it, very simple. So let's go back to the trainer, manage faults here, and I'm now ready to do a demonstration. So here we go. Let's say this cylinder has a vertical downdrift. So let's put this back, this line back, so we can start with a clean sheet of paper. Excuse my back for a moment while I put this all back together. And here's what I'm going to do. I'm going to raise the cylinder. So let's go back. Let's raise the load itself. And as you can see, I go back to neutral. Obviously, everything's good. Now, what we're going to do this time is we're going to generate a fault inside the cylinder. So let's go and create a real-time leak inside the hydraulic cylinder. So I'm going to go to my double rod cylinder, which is right over here. That's a double rod cylinder, and I'm going to raise the load. Here we go. And as you can see, I have a vertical downdraft. Now, once again, we've got two suspects. Suspect number one is the cylinder seal, and suspect number two is my directional control valve. All right. Let's take the load down. All right. Now what I'm going to do is I'm going to make sure my machine's locked out and tagged out. I'm going to de-energize and verify. And all I'm going to do is I'm going to take the bottom port of the cylinder. I'm going to take it off. Again, be safe. Follow all the recommended safety procedures. I'm going to connect my Microleak test pump to the bottom port of the cylinder. I'm going to close the valve, and I'm going to attempt to raise it. Now, if the directional control valve ports A and B are closed, then you might get a false positive. In other words, let's say the seal's leaking, but there's nowhere for the oil to leak to. So as I pressure up, the oil goes past the seal, comes back to the directional control valve, but the directional control valve is closed on that port. Well, that's not going to work. So I would recommend when we're testing a hydraulic cylinder to always remove the two lines. Bear in mind, you're going to lose a lot of oil because the load is always down on the ground. It's a safety feature. I've locked, if it's an articulated machine, I've locked it, I've chocked it, I've blocked it, I've put my locking mechanism in place on my steering, and I've made the machine safe. So I'm now going to take, just to make the point, I'm going to take the line off the live end of the cylinder, and since I'm using quick disconnects, I'm going to connect it to tank. So just to review, I've gone from my Microleak tester to the base port, the bottom port of my directional control, of my cylinder, out of the live end, and I'm going back to the tank. Now, let's see if the seal in the cylinder is leaking. I can see the rod is moving ever so slightly, but I can see that's about it. I know definitively that the cylinder seal is leaking. You see, only a matter of 15, 20 minutes, and I've now determined that this cylinder is leaking internally. So I now know what to do. So you can see how effective microleak testing is. You can test 98% of the components in any hydraulic system without starting it up. It's the safest and most efficient way to test hydraulic components. Finally, what I'm going to do is I'm just going to show you how quickly you can test a pressure relief valve. Bear in mind that if a pressure relief valve is leaking internally, you can still set it. I said that earlier on. So let's do a quick test on oh, by the way, let me just take the fault out of the cylinder and see what it looks like when the cylinder seal is not leaking. This little pump will actually lift it up. So you can see now the load is going up. See that? The load is going up. So I know in that particular instance, I would have a problem in my directional control valve if I had a vertical downdrift. This is very simple, very straightforward, and it's easy to follow through with it. By the way, the Microleak test kit, unfortunately, I invented the technology, so therefore I'm the only guy in town that's got the kit. And so obviously any schools or colleges that are interested in introducing Microleak testing will be very kind to them if they want to get Microleak test kits into their classroom, or at least one, so they can start showing students on actual equipment. If you've got equipment that has been loaned to you or been given to you by a manufacturer, you can actually teach students how to do Microleak testing on that equipment, even though you won't necessarily be able to create a fault. At least the student can get to see how effective Microleak testing is. So here's a pressure relief valve. I suspect the seat is leaking. And this is how quickly I can figure out the condition of the seat in this pressure relief valve. So here we go. I'm going to pressure in. And as you can see, I'm building pressure. It's going to drop off very slowly because it's a pilot operated relief valve. It's got a lot of moving parts. And so I'm seeing it's a slight decrease in pressure, but I did get resistance. The minute you get resistance, the component is a keeper. For each 100 psi, I lose pressure. If I look at my gauge and I've gone from, let's say, 900 psi to 800 psi, I've only lost 2 drops of oil on average. That's all I'm losing. So the published leakage rates in pressure relief valves are sitting at about 6 to 10 drops per minute. So I call that a zero leaker. This is very interesting. It's very scientific, and of course, number one, it's the safest way to test hydraulic components in existence. When you think about it, there is no other way. And let me just mention briefly thermal imaging. Many people ask me, "Why, Rory, why don't you talk more about thermal imaging using heat, a heat source?" Well, that's fine. On what? First of all, are you trending it? In other words, if I walk out to a hydraulic system and I put a thermal image on the relief valve and it's hot, how do I know that the relief valve is not part of the action? In other words, if I've got a fixed displacement pump and I'm regulating flow, what doesn't go through the flow control valve is going across my relief valve. It's going to be hot anyway. So I have to trend in order to get a reliable outcome. All right? What about this? I spoke about the directional control valve here. There's 22 valves in here. They're all within 3 inches of each other. 22 valves. If I put a thermal image on here, I'm going to get heat. But where's it coming from? Is it the spool of bore? Is it the cartridge? Is it the seal? Where's it coming from? You see, there's the problem with heat. You can't find the problem. You can't pinpoint the leakage path. I would use heat as, let's say, if I trended and I knew the system, I'd use heat as a guide. Maybe I'd start testing there, but I would never assume that that's the problem. Let's take a cylinder. You got to be very careful with cylinders. First of all, how close to the cylinder do you need to get with a thermal imager? Are you going to stand on a tire, a step ladder? You probably don't want to do that. And here's another problem. On some machines, like excavators, you've got cushions inside the cylinders. And what happens when the cylinder is all the way up, remember you have to test in the opposite direction to which you're drifting. When the cylinder is all the way up and you're deadheaded, this is when you should be reading leaks, the cushion will shut the flow off altogether. So you're not leaking at all. It's only leaking, it's leaking down, but you can't see any evidence of heat or leakage because the cushion has camouflaged the problem. So there is really no other way. When you think about it, I encourage you, if you have another way to do it, contact me and tell me what it is. But, well, you'll find out in a real hurry that there is no alternative. I've been teaching microleak testing for 3 decades, and I've taught some of the brainiest people in our country, and there are many of them, and they've never, ever said to me, Rory, there's a better way to build this mousetrap. What we need in the field are 2 things, safety and simplicity. And Microleak testing offers both. Thank you, Dactic, for everything you do, for putting this together. So you take care and be safe.
Okay, that concludes another session of the Western Wheels Conference. A big thanks to our presenters. Don't forget to request your certificate if you need one, and we'll see you around next time.